All right, here we go. Day 4 of our final exam cheat sheet development. This video is going to cover questions 16 through 21, the last 6 questions on your final exam. All of these questions are going to come from Chapter 5. Chapter 5 had to do with probability. Probability, again, is a measurement of the likelihood of an event happening. So we're going to get lots of fraction results here, where probability is measured with the number of favorable outcomes in the numerator over the number of total possible outcomes, the realm of that universe, in the denominator. Okay, so these next 6 problems are going to cover stuff like that. For these first 2 problems, problems number 16 and 17, we're going to start with 16 right here. They're both going to be based on Chapter 5, Section 2. Chapter 5, Section 2 dealt with independent versus dependent events. Basically, if I have multiple things happening in a given situation, in some cases, like what we're going to explore in these next 2 problems, one event to the other has a direct effect on possible outcomes from one to the other. Okay, and the example that we dealt with in Chapter 5, Section 2 dealt with picking a card from a standard 52 card deck. Now, I will make sure that on your final exam, you have like a resource where it kind of breaks down what all is in a 52 card deck, for especially anyone that's less familiar with decks of cards and that sort of thing. So that will not be held against you in that case. So you can actually look at what elements are in a 52 card deck. But many of us are already familiar with it, so I'm not going to go too deep into that right now. But in this case, we're going to be picking 2 cards from a standard 52 card deck of cards. And each of those selections in this problem, we're going to be replacing each of those cards once we are finished picking it. And that ends up being the major operative within this problem. The fact that we are replacing our first selection after we pick it, whatever we pick. So that means with each selection, there is a full deck of cards. This is what we would call independent pair of events. Okay, this is an independent pair of events. Basically, whatever I pick with the first card, it does not matter what happened because it's going right back into the deck, so that it's completely, the second event is completely independent of whatever happened with the first event. Okay, this is an independent pair of events. So what will you be actually tasked with doing? Now, this with replacement element will end up being the major player in for how we calculate total probability. But let's just break this down into the 2 separate things that are happening here. The 2 events that are happening are each a selection of a card. And you're going to be tasked with finding the probability of a given outcome. So you're going to see this probability notation. That's really just an abbreviated way to say something. But essentially, we're trying to find the likelihood or the probability that we select 2 kings with these 2 selections. So I want to pick 2 cards out of a deck of cards, and I want them both to be kings. I need to find the probability of that. So there are technically 2 events happening here. Our first event is the first selection, the first pick. And the probability of this first event of me picking a king is going to be expressed, as with all probabilities, with a fraction. All right. And in this fraction, the denominator is going to represent the entire realm of possibility. What is the total sample space here? And in this case, it's going to be the entire 52 card deck. So in this case, I have 52 unique possibilities to choose from, 52 cards. The numerator is going to represent what we call the favorable outcomes. In other words, my measurement that I'm trying to figure out the likelihood of here is I want to pick 2 kings. So with my first selection, I want to look for the likelihood of picking a king. And so I want to know how many ways there are to pick a king. And for those that don't know, there are 4 kings in a deck of cards, 1 for each suit: hearts, diamonds, clubs, spades. And so there are 4 total kings out of a deck of 52 cards. So my likelihood, my probability of selecting a king is 4 out of 52. Now, one thing you're going to be asked to do on your final exam is to reduce this fraction if possible. 4 does go both into numerator and denominator. It would reduce down to 1 out of 13. This should be a familiar fraction for all the examples we did that were based around cards. Okay, so the first selection, the likelihood, the probability of me selecting a king with my very first pick is 1 out of 13. Okay, but I am picking 2 cards here, so my second event is going to be my second selection. And ultimately, I want to figure out what's the probability of me not just picking one king, but two kings. All right, but let's first deal with the second selection. Again, I'm going to be calculating out a probability. Again, the denominator is going to be my total realm of possibility. How many cards am I selecting from? The numerator is going to be representing the favorable outcomes. In this case, how many kings are there in that deck of cards? But again, let me go back to this element, the fact that we are replacing the cards, because whatever happened here, whether I picked a king or not, whatever I selected is going right back into the deck for my second selection. So it's actually possible I picked the same card again. Okay, but in this case, what I'm trying to do for this probability is, again, for the sample space, because I put that card back, there are still 52 total cards in that deck. So my denominator, my total sample space has not changed. And for my second selection of another king, again, my numerator is going to represent how many favorable outcomes or how many kings are left in that deck. Well, even if I picked a king with my first selection and I was lucky enough to get the 1 in 13 chance of doing that, I would put that card back, king or otherwise. So that means out of this 52 cards, there are still 4 kings. So there is still a 4 in 52 chance of me selecting another king because I replaced that card back into the deck. And so again, I would check to see if this reduces. Just like the other one, it does in fact reduce to 1 in 13. So for each individual selection, there is a 1 in 13 chance of selecting a king. But how do I find out the total probability of selecting 2 of them? So not only to do it in event 1, but also in my second event as well. So how is that calculated? In this case, it's a simple multiplication problem. Whatever result I got from my first event, my first pick, my first selection, I'm going to multiply that result by whatever I got from my second pick. In this case, it's just going to be 1 over 13 times event number 2's probability, 1 over 13. So in this case, when I multiply fractions, just be where I go numerator to numerator, denominator to denominator, just multiply straight across. 1 times 1 for the numerator is 1. 13 times 13, you can do this on a calculator. Don't feel like you have to do it in your head, but it comes out to 169. So what's my total probability of selecting 2 kings with replacement? 1 out of 169. In other words, if I were to pick 2 cards in a row 169 times, I would only likely pick 2 kings one of those times. Very unlikely event. Okay. So that's the probability of not just picking a king, but picking a king twice. All right, 1 in 169. And again, this is with replacement. Just to prepare you again for your final, what will change, okay, for the record, on your final exam, it will not be picking 2 kings. There'll be some other scenario that happens here. Okay, it will not necessarily be another card. It could be something like saying like probability of selecting 2 of a given suit. Okay, like 2 hearts. It could be something like picking 2 even numbers, 2 face cards. Okay, there are different situations out there that can be there. And so what will change there is in each of these cases, I'll tell you that the denominator will essentially be that deck of cards. So the denominators will be the same. Okay, it's going to be 52 total cards. But what will change in your case will be the numerator, the number of favorable outcomes. It's going to depend on what you're actually measuring the likelihood of. In this case, it was kings. Be prepared for your final. It may be something else. All right, so that's problem number 16. Problem number 17 is going to be very, very similar. All right, so for problem number 17, the wording on this is going to be almost exactly the same with one small change. Now I'm not going to be replacing the card. So now I'm going to be picking 2 cards without replacement. What does that mean? So I pick a card, but I'm going to keep that card. And now that I've kept that card, when I pick my second card, there is a fundamentally different sample space that I'm picking from, whatever I selected first. And so for your final exam, for problem number 17, not only is the wording going to be the same, except for this change of phrase, but what you're measuring the likelihood of will also be the same. So for this problem, we're also going to be trying to pick 2 kings. Again, for your final exam, this situation will differ depending on what you get, whether you're picking 2 of the same suit or 2 even numbers, 2 odd numbers, 2 face cards. Okay, there's going to be a different sample space that you're measuring there. But in this case, everything else will be the same as problem number 16, with the exception of the fact that we're going to be keeping each card that we pick. All right. So now that I am not replacing these cards, let's see what happens to our probabilities. There are still two events here. Event number 1 is our first selection, and you're going to see that there's nothing different with this guy. For my first event, I am still going to get a fraction. There are still 52 total cards in a deck of cards, especially for my first selection. Nothing's really changing there. And in this case, again, I'm measuring for kings. Yours will be different for your final. There are still 4 kings in a deck of cards. So my probability of selecting a king first is still 4 out of 52. This still reduces down to 1 in 13. Nothing's really changed yet. But here is where it's going to change, because whatever I pick here, king or otherwise, I am not replacing it. So that now for my second pick, this second event here, I'm still measuring a probability. So I'm still going to get a fraction result, but here's what's going to change. Whatever happened with this first pick, I have now kept that card, meaning my total sample space has gone from 52 to 51 total cards, because there's one less. Had there been a third pick, then there'd be 50 total left over. Had there been a fourth pick. Okay, we're basically representing the equivalent of like dealing out cards in a card game. Okay, but now also favorable events. My job here is to figure out the probability of picking 2 kings. So I'm going to assume that I picked a king with this first event, meaning that if I picked one of those 4 kings, there are now only 3 remaining. So notice that both these pieces changed in this scenario. Because without replacement, this is fundamentally what we're going to call dependent events. Because event number 2 directly depends on what happened in event number 1. And so on and so forth, if there are more events. But again, I would check to see if this fraction could reduce, because this is my probability, but I want to make sure it doesn't reduce. This is one of my favorite fractions, by the way, because it does in fact reduce. Not a lot of people know that. It reduces down to 1/17, in case you're wondering, because 3 does go evenly into 51 17 times. So what you can see is that there are 2 different probabilities, 2 different likelihoods happening. That's what makes this a pair of dependent events. Okay, but at this point now, it's the exact same as problem number 16, where in order to find my total probability, I got to multiply these guys together, so that likelihood of picking a king with my first card is still 1 in 13. I'm going to multiply that by the likelihood of me selecting a king with my second card, in this case now 1 in 17. And when I multiply these together, just like the last one, I'm going to multiply numerators together. 1 times 1 gives me 1. And then 13 times 17 is going to give me, don't feel like you have to do that stuff in your head. I don't know off the top of my head. So 13 times 17 for my denominator is 221. There is a different probability because I did not replace a card. But this is my ultimate probability for selecting 2 kings without replacement. In other words, I am keeping each card as I pick it. And that is problem number 17 about dependent events. All right, let's move on. All right, these next 2 problems are going to be from section 3 on two-way tables. So for the record, I'm going to erase this in just a second, but we are going to be doing these next 2 problems from chapter 5, section 3. Chapter 5, section 3 dealt with two-way tables and probability. Basically, a two-way table is just going to be an organizational structure that is kind of a way that I can organize data, okay, raw data, for instance, like a survey, like this problem is going to be about. And so for this problem, number 18, and for number 19, you're going to be given a scenario. Okay, I'll tell you right now, it's going to involve some sort of survey that's taking place in a given area. And it's going to be split up into 2 categories. Their survey answers and in the region that they came from. And so this is going to be the result for our two-way table. Essentially, what you're going to be tasked with doing here is filling in the gaps of this table. And the reason I'm erasing the indice is because I need all the space I can get. All right, let me show you what you're going to see. So you're going to be given a table as follows. Let me try and make this nice and neat. And in this table, it's going to be organized into rows and columns. Not bad. All right, so up here for your columns, it's going to be separated by region. For instance, east versus west. So a survey is being done and we're splitting it up to east versus west, and there's going to be some total amount that happens. Your rows are going to be split up into answers to that survey. In this case, we'll keep it simple, just simple yes and no's on the survey. So 1 of 2 options with the total as well. So again, the way to interpret what's happening here on this chart, everything raw data in these columns is going to be basically separated out by region, okay? Whereas everything in these rows is separated out by how they responded. And the numbers that we're going to see in each of these squares is going to be basically how many people did whatever. Meaning that, for instance, reading this total by total box, this guy right here, this number is going to represent how many total people were surveyed in this result, regardless of region or what they responded with, okay? So what you're also going to be given on number 18 is you're going to be given some of the boxes that are just given to you, right? For instance, a 9,400 here, and your numbers will be different on your final exam. What does this 9,400 mean? That means that of all the people that were surveyed, and again, we'll see that number down here in this box, but 9,400 people said yes, that also lived in the eastern region. That's how that's interpreted. And you'll see the other stuff like this. So there may be like an 11,000 down here. Again, you'll see different numbers for your final. This literally means that in the eastern region of all the people that were surveyed, whether they said yes or no, the total number of people in the east are 11,000. Okay, you may be given something like this, like maybe the total number of people in the west is 9,000. Right? Again, you'll see a different number. Maybe 1,800 of those 9,000 people said no on the survey. And then one more box. Let's go with this guy. 16,600 people total of everyone that was surveyed responded yes, regardless of region. So that's how you'd read those boxes. What you're going to be tasked with doing in this problem number 18 on your final, you're going to be tasked with filling in the blanks. I have 4 boxes to fill in here. This is actually going to be a very, very simple mathematical operation. We're just going to be doing arithmetic, basically. Namely, for instance, say this box. If I want to know how many people in the east said no, I can use these 2 results here to figure out where that came from. For instance, there are 11,000 total people in the east. If 9,400 of them said yes, I could just figure out what's left over for who said no. Mathematically, how do I solve that? I take the 11,000 total people in the east and I subtract the 9,400 people that said yes, and that will give me how many people said no in total, and that number would be 1,600. Okay, again, you may get unfriendly numbers in your final exam where they're not quite as friendly with the zeros and stuff. It's still a subtraction problem. It's still just the arithmetic. Okay, well, what about this guy? Same sort of process here. I had 9,000 total people in the west. 1,800 said no. I can just figure out what's left over for who said yes. So I would take that 9,000 and I would subtract out that 1,800 to figure out what's left over. And if I did that, I would find out that 7,200 people in the west said yes. All right. And now for my total columns, this is where it's going to be a slightly different thing. These will not be subtraction. These will actually be addition, because what this box represents is how many total people said no, regardless of region. And for that, I just have to add these 2 guys together. So 1,600 plus 1,800 would be how I'd calculate this box. And when I add those 2 together on a calculator, it would spit out 30,400 people said no. Now, for this box, I have a couple options. I could add up the numbers in this column. I could add up the numbers in this row. It doesn't really matter, but I should get the same result. That, well, I'll just go ahead and add up the row. 11,000 in the east plus 9,000 in the west. That tells me how many total people were surveyed. In this case, 20,000 people were surveyed for this result, whatever that was for. Again, you'll be given the situation on your final exam. The situation matters less than how to calculate these guys out. But again, just notice the difference between doing a subtraction problem in these cases versus adding them in these guys. You will have a different arrangement of which boxes have been given to you. So don't expect the same kind of results here. For instance, like I could have left this guy blank and you'd have to solve for him. Or I could have left that guy blank, you'd have to solve for him. Okay, so just be prepared for those variations, but essentially this problem breaks down to arithmetic. And that's problem number 18. It's called a joint frequency table, a two-way table. And our next problem, problem 19, is actually going to be using the same exact table, but now we're going to be getting rid of these guys, our entries. Okay, so first things first, these boxes that I'm erasing, these ones were given to us in this problem. And in this next problem, in problem number 19, we're going to be asked to do what's called relative frequency. But these boxes, since they were given to you in the last one, are simply going to be crossed out. In other words, you don't have to do anything with these guys for problem number 19. Okay, and these guys will be blank, just like they were in problem number 18. For this example, I will point out again that for your final exam, you may get different blanks for different positions of these squares. So don't expect the exact same situation as what you're looking here. Okay, but this is what you'll pretty much see for problem number 19. So again, for like indexing purposes on your next space on your scratch work and that sort of thing, we are now officially going to be starting problem number 19, where these on problem number 18 were given to you with actual numbers. Now for problem number 19, they're just going to be blank like this. They're going to be filled in so that you don't have to do anything with those boxes. You're still going to be tasked with the same kind of purpose here, where your job is to fill in the missing pieces. But for this table for problem number 19 on your final is going to be called our relative frequency table. What does that mean? Essentially, in this case, this is going to be the same kind of information. Obviously, it's still the same regions. It's still the same answers on the survey. It's actually going to still be based on the same data. But now what we're going to be doing is that whatever values we got in the last problem here, we're going to end up dividing that number by whatever the total number of people surveyed was. Essentially, what we're doing is we're figuring out what percentage each of these boxes are of the total amount. So again, just for your indexing purposes, if you want to throw the stuff in the upper left-hand corner and stuff, this is now problem number 19. This is still from chapter 5, section 3 on two-way tables and probability. All right, so let me write down our raw numbers really quickly that we got in problem number 18 here. Okay, so this guy was 1,600. This guy was 7,200. This one was 3,400. And this total amount down here was 20,000. Those were the raw numbers that we had in our previous chart. What we're going to be doing with these numbers for this problem, problem number 19, is each of these individually, I want to divide them by whatever the total amount was that was down here in the lower right in that previous example. Now that total number happened to be 20,000. What I'm essentially doing with this measurement, again, is figuring out what portion of that 20,000 is this 1,600? We're figuring out portion sizes. So I can figure out like what percent of people in the East that said no were out of everyone that was surveyed, that sort of thing. So for each of these boxes, I'm going to do the same operation, a division problem, but a division problem with whatever value was down here. In this case, it was 20,000. In your case, for your final exam, it will be a different number. Whatever number ended up in your lower right-hand corner, that's what you're going to divide by. In this case, it was 20,000. So let's deal with the obvious one first here, and that's this guy. Anytime I have a number divided by itself, that's 1. And it actually makes sense where I'm talking about portion size, basically. What portion of 20,000 is 20,000? Well, it's all of itself, or what we'd also call 100% of itself. Okay, if I wanted to convert this into a percentage, I would just move the decimal point twice, and that would create 100%. And it makes sense that 20,000 is 100% of itself. All right, but these other ones will be a little more interesting. So again, don't feel like you have to do it in your head. Use a calculator. So for instance, for this guy right here, 1,600 divided by 20,000. Let's see what happens on the other side of that. Comes out as 0.08. That 0.08 represents, again, a portion of the whole amount that this box represents. If I were to convert that into a percentage and move the decimal point over right twice, this would represent 8% of everyone that was surveyed met that requirement, namely saying no and from the East. For this box, now I do 7,200 divided by 20,000. That gives me 0.36, a bigger portion. voted here. And lastly, this guy, again, just dividing by the 2,400 or 20,000 again. 3,400 divided by 20,000 gives me 0.17. What does that literally mean? If I were to convert that into a percentage, that'd be 17% of everyone that was surveyed said no. Okay. But that's all you had to do for problem number 19. Again, it's based on the results of problem number 18. So just be prepared for that as well. It's the same exact scenario, but they are closely tied together. But that's problem number 19. All right, let's keep going. Our last two problems of the final exam are both going to come from the same section, just like these the last other two pairs that we just did. These are both going to come from Chapter 5, Section 5. Chapter 5, Section 5 dealt with permutation and combination. Permutation and combination. There are basic ways to count the size of a sample space, with one important distinction. Does the order matter or not? Okay, so for these next two problems, problem number 20 that we're going to do right now and problem 21, you again are going to be given the same situation. Okay, there is a race that's going to be happening, and your job is going to be to find the number of ways something happens. Okay, find the number of ways, and then you're going to be given a situation to measure. You're going to be given two pieces of information. I'll tell you for this example and for the next problem that there is going to be a number of runners in that race. For this example, we'll say there are 12. Be prepared that this number will change for yours. Okay? And really the number itself is going to be arbitrary. It kind of doesn't matter. It's still going to be just an input in a calculator. But in this case, there are 12 runners running this race. The second piece of information that you're going to be told to identify is find the number of ways about a number of arrangements of this using this sample pool. Okay. In this case, for this problem, we're looking for the ways that they're going to finish first, second, third. For this example, be prepared for your final that one, this number might change. You may have a different number of runners. And that in this example, we're only going to third, but for instance, on your final exam, you could just be like, how many different ways can people finish first, second, or first, second, third, fourth, or first, second through sixth, so on and so forth. Like these two pieces will change depending on your final. Okay. So I still need to find the number of ways. There is a fundamental difference between permutation and combination. Basically how I calculate the number of arrangements. And it has to do with order. Fundamentally in this problem, this means that order matters because first place is going to be very different than second place, which is very different and unique from third place. In other words, in this case, for problem number 20, order matters. And because order matters, that means I'm going to be using permutation, NPR. In section 5, we learned about permutation, meaning that order matters. Because if first, second, and third are what I'm actually trying to measure, those are very unique, distinct positions. In other words, order matters, so I'm going to be using permutation. And this is a calculation button on a calculator. I'll show you that in a minute. They're really just two pieces of information I need to be able to fill in here, N and R. N is going to represent the total number of possibilities. Basically, the number of options I have for this scenario. In this case, the fact that there are 12 runners. N is going to be 12. These are the number of options I'm going to be choosing from. R is going to represent how many objects I'm actually choosing. In this case, I'm looking for first through third finishers. In other words, I'm picking 3 of those 12. Okay, so in this scenario, it's 12P3. Be prepared for your final that this number could change, and that's going to represent this N value. And the number of positions I'm caring about might also change, and that's going to change this value. Okay, now in our notes, we learned about a formula involving factorials, namely a permutation is this calculation where I do N factorial over N minus R factorial. This is the long way about solving it, but I'm going to be okay with you using a calculator. So as long as you can show me this, Now I'll show you how you actually go about solving it on a calculator itself. All right, so on a calculator, let me show you this really quickly on my scientific calculator. You'll notice these two buttons. Notice the NPR in yellow right there and the NCR in yellow right there. NPR refers to permutation, or order matters. That's what we're going to be using for this problem. On problem number 21, order is not going to matter, and we're going to be dealing with combination. So be prepared to locate these functions on your scientific calculator. If you need help identifying it, just make sure you ask me. I'm not going to like hold it against you if you don't know how to do a certain operation on your calculator. So if you ever have a question about how to use a calculator to perform a certain function, ask, even during the final, because that will not be something I hold against you. All right, so how do I do this operation where in the calculator it's going to do all this mess for me? The first thing I'm going to start with in my calculator is my n value. In this case, the fact that there are 12 total racers. Again, this number will be different for you on your final. Now I'm going to be using the NPR function, which if you recall was this button right here, but it's my secondary function. So just be sure to be able to locate your NPR button on your calculator. And now it's waiting for me to put in the R value, basically how many objects are being selected out of that. In this case, I'm going to care about the first three places, first, second, third. So I'm picking 3 out of those 12, which gives me 1,320. What do I do with that number? That tells me the number of ways that I can select first, second, third out of 12 racers. 1,320. That's a lot of different combinations right there. A lot of different permutations, rather. All right, and that's problem number 20. Problem number 21 is going to be almost the same exact situation with, again, one fundamental difference. So let's prepare for that. Last problem of our final exam prep will also be from Chapter 5, Section 5 on permutation and combination. But in this case, there's going to be one fundamental difference. Instead of first, second, third, I'm just going to care about, in this case, say something like this: 3 qualifiers. So for those familiar with track and field, okay, and these kinds of races, when I have like a final race and like we're giving out medals and stuff, gold, silver, bronze, and that sort of thing, that was like the last problem, problem number 20, where I'm caring about the difference between first and third, for instance. In this case, now first through third are all just going to be qualifiers. In this case, order does not matter. If I finish third in this race, I still qualify to go on to the next race, because now in this case, my position, my finishing order does not matter. So order doesn't matter in this instance for problem number 21. And because order doesn't matter in this case, I'm going to be using NCR, or combinations. Okay. So in this case, because of the fact that all 3 are qualifying and it doesn't matter who finishes first or third or second, they just all simply qualify for the next race. That's why I'm going to be using combinations. I still need to identify N. I still need to identify R. Well, N, again, is the number of objects I'm selecting from. In this case, again, it happens to be 12 total racers here. So N is 12. R is how many people I'm going to care to select the objects from, and that happens to also be 3 in this case. And so I have this 12C3. Now, again, for the record, there is a formula for this that we learned in the notes, and that was n factorial over n minus r factorial times r factorial. Pretty complicated thing, but here's the good news. This mess is actually a button on the calculator that can be done for you. So let me show you how to do that really quickly. And again, the difference is really just being able to tell when does order matter or not. So on a calculator, scientific calculator, I pointed out last time, but this NCR button is what I'm going to use in this case because order does not matter. Okay, so now the same kind of order of things that I plug into this calculator are going to be the same. So I need to start with N, that's 12. Now I'm going to hit the NCR function. So I have to do my secondary NCR. It's now waiting for the R value, which is 3. I'm picking 3 out of the 12. It doesn't matter what order they're in. And now this tells me that there are 220 ways to just pick 3 people out of these 12, regardless of order. And that's the last problem on our final exam. Again, just be able to distinguish for when does order matter or not. All right, but I'm going to go ahead and stop recording there. We have officially gone through all 21 problems. Best of luck.